Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on September 9th, 2025, which was just 2 days ago. The big headline is Speed with Quality. It keeps the RayGauss volumetric rendering accuracy while cutting training time by about 5 to 12 times and boosting rendering frames per second by about 50 to 80 times on real-world datasets. The paper is titled RayGaussX, Accelerating Gaussian-Based Ray Marching for Real-Time and High-Quality Novel View Synthesis. And as we will see later, the results are really impressive. Beyond speed, it improves distant scene coverage and slightly raises image quality, approaching Gaussian splatting visuals while remaining far faster than grid nerfs like ZipNerf. On X, a post highlights empty space skipping, adaptive sampling, and ray coherence improvements that speed rendering while preserving quality, with a demo clip and about 100 likes indicating solid engagement. Also, the author shared a GitHub repo, but it currently looks empty. Listeners will find an empty repository with no code or examples, just the project placeholder. It suggests the implementation is forthcoming, so interested folks should check back for updates as the code and docs get added. Alright, the previous segment spotlighted the speed gains and outdoor improvements. Figure 1 compares renderings on the garden scene with panels for ground truth, RayGaussX, RayGauss, ZipNRF, and 3DGS. RayGaussX shows sharper bricks and windows than RayGauss while running far faster, which matters because details survive without the heavy cost. ZipNRF looks crisp but runs at a fraction of a frame per second, whereas 3DGS is fastest but slightly blurrier. Alright, the previous figure contrasted visual quality. Figure 2 presents the key speedups: empty space skipping with adaptive sampling, Z-order curve reordering for memory coherence, and a regularizer that shrinks the axis-aligned bounding box to ellipsoid volume ratio so rays hit fewer false positives. The left panels illustrate longer steps through transparent regions, the center block shows spatial reindexing, and the right panels depict isotropy reducing oversized boxes. Together, these changes cut work without sacrificing detail. Well, the previous figure outlined why the method saves work. Table 1 compares NRF synthetic performance across quality and speed, and it shows that RayGaussX edges out RayGauss on PSNR and matches SSIM and LPIPS while training in 22 minutes versus 33. The big shift appears in speed because frames per second jump from about 25 to 85. Competing splatting methods render fast, but they trail slightly in fidelity. So while the previous figure explained the mechanisms, Table 4 quantifies their impact on the garden scene. The table shows that the new densification alone raised PSNR to 28.38 and slightly sped training and rendering. Empty space skipping plus adaptive sampling lifted frames per second to 5.9, and the isotropic loss pushed it to 10.1, which mattered because rays skipped false intersections. The full combination reached 27.4 frames per second with 84 minutes training, while maintaining similar perceptual metrics. So the previous figure unpacked mechanisms. Table 3 reports head-to-head results on 3 datasets. The table shows that RayGaussX delivers higher quality than RayGauss on PSNR and SSIM, while boosting frames per second from roughly 0.5 to 24 on MIP-NRF 360 and to 41 on tanks and temples. Rendering quality also edges past spec Gaussian on MIP-NRF 360, which matters because rasterized splatting slows as quality add-ons accumulate. Training times drop sharply versus RayGauss, yet image fidelity remains competitive with ZipNRF. Alright, 2 takeaways stand out. It delivers real-time rendering with strong fidelity by skipping empty space, adapting sample steps, and reorganizing rays, and it fixes distant scene under sampling through distance-weighted densification and scale regularization. The broader implication is practical interactive novel view synthesis on large real scenes. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.